As a teacher, if you've ever been questioned about how you teach math, or perhaps why you teach certain strategies, because it would just be easier if you used the one that we all learned back when we were in school. Yeah, that happens to all of us. In today's episode, I want to talk a little bit about new math and why we teach so many different strategies to help kids solve number problems. Well, I would argue that being good at math is not about speed, and I know that that is supported by lots and lots of research. We do need to be competent mathematicians and be able to solve most number problems that we encounter in our daily lives. We should have strategies to solve in our head. Now, this is where new math comes in. The thing is that new math isn't new. It's simply making explicit all of those mental math strategies that you use in your head, making them explicit and showing students what happens on paper. Because the reality is not everybody is just going to naturally solve out how to calculate equations in their head. Some people need explicit instruction to be able to figure out how you can break apart numbers and make things simpler, easier, and friendlier. That is the goal of teaching students different ways to solve math problems. We also have to encounter that math is taught along a continuum. There is a developmental continuum that is happening here where we want to make sure that students gradually gain the skills and they kind of have to move along the path. There is some ability for students to use what they know and apply it to other concepts, but there is, generally speaking, a progression that a student would develop in their understanding of math skills. You're not going to learn how to solve complex algebraic equations before you can count to 5. So there is going to be a pathway. A lot of these new math strategies are designed to help students bridge between what they know now versus where they need to go. We are always striving to help students find the most efficient strategy. However, we also need to recognize that the path to that efficiency isn't always efficient. So we need to trust the process and allow our students to explore these concepts in a natural way that gets them from point A to point B. Now, as adults, we were not taught this way. I can guarantee you, if I had been taught that way, I would have felt much more positive about math. I am so passionate about math now because I recognize the benefits of how we are teaching math and how much of a difference that would have made to me as a student. I'm not bad at math. I just don't necessarily think about math the same way as other people do. So I need alternate strategies, and that's the other piece. We have to look at math as differentiated. We need to understand that not every student thinks exactly the same way. Not every student are going to approach solving math problems the same way. Some students will prefer to see it in front of them and manipulate it. Other students want to take quick shortcuts and find logical connections. Some students need to work through it step by step by step. They need to see every single step and understand every step completely because they're not ready or able to make shortcuts all of the time until they fully understand the whole picture. We need to recognize that if we have a wide variety of ways that students approach math in our math classrooms, then we need to design our math programs to be able to meet the most amount of students. That is why it's so important that we are teaching multiple math solving strategies to be able to add, subtract, multiply, and divide. 1, because math is learned on a continuum, and 2, because not every student thinks the same way about math, and 3, students need explicit instruction on those mental math strategies because we can't just assume that everyone's going to figure it out without us teaching them. I want to walk you through division, often a difficult one to teach, one that so many students struggle with, and it's sometimes the last one that we teach out of division, multiplication, addition, and subtraction. So I want to look at different strategies and why we use those strategies and what order I would put them in and why. And then this can be applied to multiplication as well as addition and subtraction as well. So first I want to look at where we're starting. So in order to understand division, we need to have students that are understanding that we are breaking apart numbers. Okay, so let's look at the very first strategy for division. Now, when we're talking about division, what is known versus what becomes efficient? So we're obviously going to be going from the what is known, which is subtraction, breaking up a number into smaller groups. We're breaking up the number into groups. It's the opposite of multiplication, but instead of building groups and adding them together, we are taking a total and breaking it up into smaller groups. Well, what is currently known by a student who does not understand division is subtraction, that they understand how to take away. So the very first strategy that we would teach for students that are looking at developing their division understanding is by looking at subtraction. Now, we can do this in two different ways. Number one, we can use a number line, because we want to visually show that we are taking groups away. So in this top question here, 24 divided by 6, we start over on the right-hand side with 24, and we start taking away groups of 6 until we get to 0, or until we get to a number that is smaller than 6 and we can't take another group away. We want students to start understanding that in division, we are taking away groups of things, that is the actual action that is happening when we are dividing. So by writing this out on a number line, we can show them of the taking away of groups in a repeated way. So it's a repeated subtraction. Is this the most efficient strategy for larger numbers? Absolutely not. Once the numbers start to get bigger and the equations start to become more complex, they can understand of what's actually happening because they're practiced with these smaller numbers, but then they can start moving into finding more efficient strategies. So for some students, this number line might make sense, especially if you're looking at for visual learners. You might want to teach them that they can actually have a group of 24 things on their desk and physically move things away and record it on that number line. But we are really getting them to understand that division means to break apart into groups. So the second method might be for students that want to just see the math kind of work. They're really familiar with the standard algorithm for subtraction. So we would use this to form repeated subtraction questions using the standard algorithm for subtraction, because ideally they should have that concept already built. So we can start to use that as we are approaching the division competency. So we are approaching them being competent at dividing. We start here. So we can show them 24 take away one group of 6, 24 take away a second group of 6, 24 take away a third, then a fourth, and we finally end up at 0. Then we have to show students, well, okay, how many groups did you take away? Well, we took away 4 groups. So therefore, 24 divided by 6 is 4, because we've taken away this many groups of 6. That is dividing. Again, not the most efficient strategy. If the larger numbers are encountered, yes, this process is going to take a lot of time. We also want to almost push students to understand that this is not an efficient strategy and there has to be a better way. And that's the learning that we sort of want to see is, okay, this works for these smaller numbers and it's pretty efficient, but now my numbers are bigger and there's got to be a faster way because this is taking a lot of time. And we want our students to start seeing efficiency. We want them to become more efficient, but we want them to see how that process is going to go. Now, another strategy that we can teach is also understanding the inverse relationship that subtraction and addition have with one another and starting to understand that there is a relationship between all of these operations. So we can also use what's called an open number line. This is where we start at 24, but we start to use multiplication to get to that bigger number. So in this example, we're dealing with far bigger numbers here. So this would be perhaps older students in junior grades. We have 889 divided by 24. Now, most of us probably are not looking at this and thinking, oh, I know the answer right away is 37 with a remainder of 1. That's probably going to take most of us a longer time mentally because we haven't built up that as adults, especially if we were not taught these ways. We haven't really built up that understanding of how we can solve that without pulling out a pencil and paper and using long division or using our calculator. So with this strategy, we are focusing on students understanding that multiplication and division have an inverse relationship as well as addition and subtraction. So we are going to use repeated addition or subtraction and multiplication to build up. So we're looking at how many groups can be made or how many times groups of 24 can be put into 889. So if I multiply 24 by 10, so if I have 10 groups of 24, well, now I have 264. So I start at the 24 and I say, okay, I've got, that's one group. How much do I need to add to the 24? If I add 10 groups of 24, well, that's 240 plus the original 24 I started with. So now I have 264 in all of my groups of 24. So I have how many groups? I have 11 groups of 24 now. Okay. Well, what if I add another 10 groups? Am I at 889 then? No, not yet. So I add another 240. So we have 24 is one group. Then I add 10 more groups. So now in total, I have 11 groups, and 11 groups of 24 is 264. Not quite yet at the 889. So I add another 10 groups of 24. Well, now I had 11 groups before. Now I have 10 groups. Now I have, so in total, I have 21 groups of 24. How much is that worth? 504. Then I add another 10 groups and go, okay, well, how much is that? Okay, another 10 groups of 24 is 744. So now I have 31 groups of 24, and that's 744. Well, if I add another full 240, I've gone over. So that's going to be too much. So now how many groups of 24 can I add now? Okay, well, if I add 5 more groups of 24, that's 120 because 5 times 24 is 120. So how much do I have now? What is 744 plus 120? We have 864. Well, I'm not quite there yet, but if I add 2 more groups of 24, then I go to 888, which is as close as I can possibly get to that 889 without going over. And how much is left between that 888 and the 889? Just 1. So if I add up how many groups I've added, I have the first group of 24 plus 10 plus 10 plus 10 plus 5 plus 2 gives me 37 groups of 24 will give me 888 with a remainder of 1, which means my answer is 889 divided by 24 is 37 with a remainder of 1. This is a great strategy if your students have a really good understanding of multiplication and they understand things like multiplying by 10s and 5s and 2s. Often what happens is students don't have all of their fast facts memorized all at the same time that they're expected to be learning division. Those are kind of happening together, but maybe one doesn't happen before the other one starts. So we're going to teach students how to divide possibly before they have all of their fast facts ready. So in this case, the standard algorithm actually relies on a student's understanding of knowing all of their fast facts really competently. But if you have a student that does not understand their fast facts yet, and they haven't necessarily remembered or memorized all of them, this is a strategy that can be used to help bridge that gap until they do. They're understanding division and how it's happening, but they're learning the steps. Now, ideally, this would become more efficient over time so that a student wouldn't necessarily say, okay, add 10 and then 10 and then 10. Maybe they would say, okay, I know if 10 times 24 is 240, then 10 times 30, what would that be? And they would just add the 30, and then they could add the 5 or the 6 or however many they wanted to add to use the least number of jumps on this open number line to get them to that answer. This actually is also a very good replica of what happens inside someone's head when they're solving division, because most of us flip that division to a multiplication question and figure out the missing number in that question. So instead of 889 divided by 24, it's 24 times blank equals 889. And if we're using this strategy in our heads, it's important that we teach students how to explicitly use this strategy and how to solve a division problem without having to use long division. I know so many of us hated long division as we were kids growing up. So why don't we look at different strategies that can be used where we can use what we're good at, what we're strong at, which is currently, if we're teaching this strategy, currently a student's strength would be in multiplication but not all of their facts yet because they're still developing those skills, this is a really good strategy for those students to use, which is why it's important that we teach it, because it means that more students have an accessible strategy to be able to divide. And again, you might have students that just want to do this as they're writing it out, like it's a standard algorithm for multiplication. So instead of using a number line, because maybe that's too visual for some students and they just want to like lists and organize tables, then using 24 times 10 and then 24 times 10. And it's the same process. If you're noticing the process on the bottom, it's actually the same that's happening on the number line. It's just represented in two separate ways, but it's the same strategy. Now, another strategy we would choose to teach students is called the Big Seven. It's very similar to the open number line, but it also is a great bridge between the open number line and your standard algorithm for division. It looks very similar. What you write down is slightly different, and how you record things on a piece of paper is slightly different. But this is a great bridging strategy that helps move our students from, say, the open number line and move them into being more familiar with what's happening in a standard algorithm of long division. So we want to, again, developmentally get them ready for that more efficient strategy. Now, this is still a pretty efficient strategy, and it also helps to support students that may not have all of their fast facts memorized. And if they become more efficient within this strategy, it's still one that can be used. In fact, a lot of people prefer this strategy and just would like to avoid long division for the rest of their lives. So that's okay too, but this is one of the strategies that is really important for students to be able to solve as well. So there's a few steps here. And what we want to do is rely on the fast facts that we know and are easily to record in a list. So we always teach this with a cheat sheet. We want our students to make a quick cheat sheet. Is it necessary? Not at all. When you're really efficient with this strategy, you probably don't need that cheat sheet. But again, we always start with introducing that cheat sheet because it's important for our students to start with what they know and then move towards efficiency as they get better at practicing. So for this strategy, the Big Seven of flexible division, we're going to start with a question, 387 divided by 17. Now, we already know the answer, 22 with a remainder of 13. So let's figure out how we got that answer. The first step in solving this Big Seven is to come up with a cheat sheet. We know most of our students, the very first fast facts that they learn are their 2 times tables, 5 times tables, and 10 times tables. Those are pretty standard. So we want our students to write out just very quickly what those answers are to those quick questions. So they often will not have their 17 times tables memorized, but by being able to see the relationship between these in the cheat sheet, it'll help them to understand where the bigger numbers are and break it apart. The flexible division big strategy is all about breaking apart that big number into smaller, more manageable chunks. It's very similar to what was happening in the open number line, that we were moving from left to right. In the Big Seven, we're very much moving from right to left. We're taking the big number and breaking it apart instead of starting with a small number and adding different values of groups to it. So we start with 17 times 2 because most students understand their doubling strategy. They understand that times 2 means to double. So that's a good reminder. Now, I always teach my students to skip ahead to the 17 times 10 because we know that 17 times 10 is simply just adding a 0 on the end of 17. So we know that 17 times 10 is 170 and double of 17 is 34. So it's a good start. Now we know the 17 times 5 because we simply take the 17 times 10 and cut it in half. So we're using those kind of logical connections that our students understand the relationship between a 5 and a 10, that 17 times 10 is 170, and 17 times 5, because 5 is half of 10, so 17 times 5 is going to be half of 170. So then they do the 85. Now, once they have those 3 fast facts, then we start going, okay, well, what's 17 times 20 times 50 times 100 times 200? And it's really just starting to use their knowledge of powers of 10 to add in those zeros on the cheat sheet. Now, all of their answers are going to stop when they encounter a number that is bigger than the number they're dividing. So in this case, we went to 17 times 50. It was 850. That's too much. They can stop on the cheat sheet. Step 2, once they have their cheat sheet, is to write the question in a big 7. So that's why we call it the big 7 strategy, because the little lines that you put around sort of look like long division, except it's got that tail on the back end. It looks like a big 7. So that's why we call it that. So it lays itself out very familiar to what you would teach in the standard long division algorithm. In this case, the 387 goes inside the big 7 and the 17 goes on the outside. Now, what you're simply looking at here is in your cheat sheet, what is the largest number in your cheat sheet that you multiplied 17 by that gets closest to the big number you're dividing by. So 387 divided by 17. 17 times 20 gave us 340. Well, that's pretty close. So the 20 goes on the outside of the 7. So 17 times 20 goes on the outside. And the answer to 17 times 20 goes on the inside underneath 387. And then I subtract. I've already taken away 20 groups of 17, which is 340 things total. So 20 groups of 17 is 340. Well, how many things do I have left over? If you're thinking of actually modeling this on like your desktop, how many do I have left over? I got 47. So how many groups of 17 can I make out of 47? Well, looking at my cheat sheet, I know 17 times 2 is 34. Well, that's pretty close. So 17 times 2 is 34. What's left is 13. Well, 13 is smaller than 17, so I cannot make a group of 17 out of 13 things. So I'm done. Add the numbers on the pink numbers there on the outside of the big 7. 20 plus 2 equals 22. Therefore, my answer of 387 divided by 17 is 22, remainder 13. Now, another strategy is the box method for division. This is the same thing as the standard algorithm. In fact, it's actually, in my opinion, more efficient than the long division standard algorithm. Both of them are equivalent, but they need to understand what's happening here. This is a lot quicker to write, but they do need to understand the steps in the process. One of the biggest challenges with teaching the long division standard algorithm is there is a lot of steps. And sometimes you have to memorize the steps in order to get to the answer, but you're not really actually understanding what's happening when you're dividing. So sometimes when I will look at the big 7, it'll help me to understand why I have broken apart and seeing the connections between the previous strategies that I've done and then the answers I get in both the box method and the long division standard algorithm. So we operate here very similarly. We put all of the digits of the dividend, the number we're dividing, all the numbers of the dividend are going to go inside their own individual place value blocks. So 275, just like you see there in step number 1. Now we're going to divide 275 by 7. So the first question we ask is how many groups of 7 can we make out of 2? The answer is 0. So same with long division. We first do the division. Now we do the multiplication. 0 times 7 is 0. And do the subtraction. To take away 0 is 2. Now, instead of bringing the 7 down like we would in the long division algorithm, we're going to move the 2 up. For a lot of people that are in their 30s and 40s, this may have been called short division. Now we use the box method because it's similar to what we are teaching in multiplication. But this is the box method. We're moving the 2 up. And as you see at the bottom here, we keep doing that. Now 7 goes into 27. 3 times 7 is the multiplication, 21. Subtract 27 minus 21 is 6. And then we move that 6 up to the next column. Now we have 7 goes into 65, 9, because 9 times 7 is 63, with a 2 remainder. Can't make a group of 7 out of 2, so we're done at this point because we're not teaching students to go into decimals. Now, if we are going to teach students to go into decimals, we can still use this strategy. This is a great one. Once our students have mastered this strategy with whole numbers and using remainders, it's then at that point that we're ready to teach students how to start dividing into decimals without a remainder. But again, this is a continuum. We teach them one step at a time. As they become more efficient, we can introduce more complexities, larger numbers, adding some decimals, removing the remainder. All of that is a continuum of understanding that we're helping our students to go through. And finally, the one that we all know and love, do monkeys steal bananas, or the standard algorithm for long division. And again, this is one that is very familiar with teaching, but it does require students to memorize the set of steps of divide, multiply, subtract, bring down, very similar to the box method, same rules, but it's more of a process. This is a strategy that we're going to use most efficiently for doing things like decimals and adding in decimals and understanding that we can go into the decimals instead of stopping at a remainder, that we can continue to find the answer, and that's great. Sometimes students aren't going to be able to find that remainder if they're going to do it on a calculator, so we want to teach them how to use these different pencil and paper and mental math strategies and then move them into this eventually. Again, this is all eventually. Now, these skills, again, are also built over our entire junior program. So we need to remember students in grade 3 are working with just breaking apart that repeated subtraction. As students are moving through grade 4, grade 5, and grade 6, they're moving into these skills. They can take what was learned in grade 4 and start adding more complexities to it. By the time they get grade 5 and grade 6, now they're ready to divide without remainders and start moving into the decimals. That's all that's expected of our students, and it's important that as teachers, we teach it all on a continuum because we need to recognize that students learn differently. We need to make mental math explicit for our students and teach them exactly what should and can be happening in their head to solve multiple equations. And we want to make sure that we are helping our students learn the understanding and the deeper understanding and meaning behind what they're doing. And they're not simply memorizing steps without a complete understanding of the complex math that is happening and why that standard algorithm works. When they understand that, then they're ready for the standard algorithm, but not before. And that is exactly why we teach new math, because we are trying to teach all of the understanding that a student is going to need. And we want to make sure that we are building competent mathematicians and students that don't graduate school always thinking that they're bad at math.